Hello friends, welcome to a lecture series on multivariable calculus. So today we will deal with partial derivatives. So what do you mean by partial derivatives and how we can use this solving some problems, let us see. So we start with one variable problems, function of one variable. We know that if you have function of one variable, say y equals to fx, where x belongs to R, say, then if function is differentiable at a point say x equal to a, then we say that dy by dx at x equals to a or is equals to f dash a is equal to limit h tending to 0 f a plus h minus f a upon h. So, this is how we define derivative of a function at a point say x equal to a. It is simply limit h tend to 0 f a plus h minus f a upon h. Now, what does it mean? What does it give? Derivative, it simply gives slope of a tangent at a point x equal to a. If we have a curve x y equals to f x, then at x equal to a it simply gives slope of the tangent. Okay. It also represents rate of change of f along x axis, rate at which the function changes along x axis. So, this we have already deal with, we have already seen what do you mean by function of derivative of function of single variables. Now, in multivariable we have more than one independent variables. So, we can't define derivative like this. Okay. So, here we have function of variables more than one. So, what we have here? Here we have a concept of partial derivatives. So, what do you mean by partial derivative? Let us see. Suppose we have a function of x and y, two variable function. Here x and y are independent variables and z is a dependent variable. Now, we define del f upon del x. It is simply partial derivative of f with respect to x, say at x equal to a. So, what does it mean? It is partial derivative of f with respect to x at x equal to a. Okay. Now, here when we deal with partial derivative of f with respect to x, that means we are treating all other variables constant. Okay. So, we define this as limit h tending to 0 f of a plus h. Okay. We are defining partial derivative say at a point a comma b. Okay. So, at a comma b, because here we are having two variables a and b, I mean x and y. So, it is limit h tend to 0 f of a plus h b minus f a b upon h. So, this is partial derivative of f with respect to x at a comma b. So, simply we are changing only in x component, y will remain same. That means, we are fixing y and changing only with respect to x. Now, what does it give? It simply gives rate of change of f along x axis or rate of change of f along I cap direction. Okay. Or we can define it like this: z equal to fxy is a surface, z equal to fxy is some surface. Okay. Now, y equal to b is a plane which cut this surface into a curve. Okay. Now, the slope of the tangent for this curve z equals to f x b, because y is equals to b at the point a b f a b in the plane y equals to b. So, it simply gives slope of the tangent for the curve this at a point this in the plane y equal to b. because z equal to fxy is a surface. When y equal to b cuts it, it will give a curve. Okay. And the point is this, at this point the partial derivative of f with respect to x simply gives slope of the tangent of this curve in the plane this. Okay. So, this is how we can define del f upon del x or partial derivative of f with respect to x geometrically. Similarly, when we talk about partial derivative of f with respect to y, so with respect to y, how can we define? Now, del f upon del y at a comma b, which is partial derivative of f with respect to variable y at a comma b, is simply limit s tending to 0 f of a b plus h minus f a b upon h. Now, here when we are differentiating partially f with respect to y, we are differentiating only with respect to y, keeping all other variables constant. So, here a is constant, we are fixing a, we are changing only in the y component b plus h to b upon h. So, this is how we can define partial derivative of f with respect to y. Again, geometrically, if we are talking about partial derivative of f with respect to y, it simply gives rate of change of f along y axis or rate of change of f along j cap direction, or z equals to fxy is a surface and x equal to a is a plane. When x equal to a cuts this surface, it will give a curve. Which curve? It will give this curve. Okay. And the slope of the tangent for this curve at a point P in the plane x equal to a will represent del f upon del y at a comma b. Okay. So, this is how we can define first order partial derivative of two variable functions with respect to x and y. Now, we will see some problems based on this. Let us see. The first problem is, it is f equal to 3x cube plus 4x square y square minus 6y cube. Now, suppose you want to find del f upon del x at any point x comma y. So, del f upon del x is simply partial derivative of f with respect to x. That means, you have to simply differentiate this function with respect to x, keeping all other variables constant. So, derivative of this with respect to x is simply 9x square plus, you have to keep y constant. Okay. Then this is 8xy square minus 0, because we are treating this as a constant. So, this is x times 9x plus 8y square. Okay. So, this is del f upon del x. Now, similarly, if you want to find out del f upon del y, it is nothing but, now you have to differentiate f with respect to y partially. That means, you have to take x as a constant. Okay. So, this is 0 and this is 8x square y minus, it is 18y square. So, this is del f upon del y. Now, del f upon del x is sometimes also represented as fx. Fx means del f upon del x. Now, del f upon del y is also represented as fy. Okay. Now, the second problem, the next problem. Now, f is tan inverse y upon x. Okay. Now, what is fx? What is fx? Fx simply means del f upon del x. Okay. Now, if you want to compute this, it is tan inverse something t. Tan inverse t is, derivative of tan inverse t is 1 upon 1 plus t square, and then del by del x of t, which is y upon x. Okay. This is simply equal to x square upon x square plus y square into, now partial derivative of this respect to x is, you have to take y as a constant, it is minus y upon x square, because 1 upon x is minus 1 upon x square, derivative of 1 upon x is minus 1 upon x square. So, it is minus y upon x square plus y square. So, this is del f upon del x. Now, del f upon del y is fy, which is equals to, again tan inverse t, it is 1 upon 1 plus t square, and then del by del y of t again. Okay. And it is equals to x square upon x square plus y square. Now, del upon del y of y upon x is simply 1 upon x. Okay. And this is nothing but x upon x square plus y square. So, this is how we can find out del f upon del x or del f upon del y for some function of two variables. Okay. Now, let us solve second problem. Find zx and zy if the equation this defines z as a function of two independent variables x and y. So, what is the function? Now, the function is, equation is x square plus y square plus z square plus 6xyz equal to 1, and here z is a function of x and y. X and y are independent variables and z depends on x or y, x and y. Now, how can we compute zx? How we can compute zx and zy? This we have to find out. Now, we simply differentiate partially with respect to x. So, differentiate partially, say this equation is equation 1 with respect to x. Okay. So, what we will obtain? You see, x square is 2x when you differentiate partial respect to x. Y square is, because x and y are independent. Since x and y are independent, so partial derivative of y respect to x will be 0. Now, z is a function which depends on x and y. Okay. So, partial derivative of z respect to x will not be 0. It is t square means 2t, that is 2z into del z upon del x, okay, plus 6 times. Now, when we differentiate partial respect to x, we will take y as constant, because y is independent of x. So, we can take y also common. Now, inside bracket we are having x and z, and both are the function of x. So, we have to apply product rule, that is, first as it is derivative of second, that is del z upon del x, plus second as it is derivative of first, and derivative of 1 will be 0 with respect to x. Okay. So, what we will obtain from here? Now, let us collect del z upon del x. This implies del z upon del x. Let us collect these terms, 2z plus 6xy, which is equal to the remaining terms put it on the right hand side, it is minus 2x and it is minus 6yz. Okay. So, what we are having, this implies zx is equals to, you can cancel 2 from both the sides. So, it is minus of x plus 3yz upon z plus 3xy. So, this is del z upon del x. Now if you want to find out del z upon del y, so similarly we can proceed for del z upon del y. Now again differentiate partially equation 1 with respect to y. So, what we will obtain? Now, x is independent of y. So, partial derivative of x with respect to y will be 0. So, this is 0 plus y square, the derivative, partial derivative of y with respect to y is 2y. Of course, del y upon del y is 1 plus 2z into del z upon del y, because z is a function of x and y, z depends on y, okay, plus now 6x you can take common, now y into z, and both are the function of y. So, you have to apply product rule here. So, it is y into first, as it is derivative of second, it is del z upon del y plus z into 1, which is equals to 0. So, this implies, now collect terms of del z upon del y, which is 2z plus 6xy equal to, put all the remaining terms on the right hand side, that is minus 2y minus 6xz, okay. Cancel 2 from both the sides again. So, this implies zy will be equals to minus y plus 3xz upon z plus xy 3xy. So, this is del z upon del y. So, that is how, if some implicit equations are given to us, we can easily compute del z upon del x or del z upon del y if z is a function of x and y. Now, we will solve some more problems where f is a function of 3 variables here, okay. The same definition will applicable for 3 variables also. If we have function of 3 variables, suppose you want to compute, suppose you are having w is equals to f x y z. Now, here x, y, z are independent variables and w is a dependent variable, okay. Now, if you want to compute del w by del x, or we can say del f upon del x, or we can say wx, okay. So, this simply means we are treating x as a variable, all other variables as constant, okay. Suppose you want to define del f upon del x at some point, say a, b, c. So, how can I define this? It is limit h tending to 0 f of a plus h b c minus f a b c upon h. The same definition which we have used in for 2 variable functions, the same will be followed for 3 variables or more than 3 variables, okay. Similarly, we can define del f upon del y or del f upon del z. Now, we will solve some problems based on this. Now, suppose f of x y z is, the first problem, it is ln x plus 3y plus 6z. So, what will be fx? Fx is del f upon del x, okay, and it is log t. Log t is derivative of log t is 1 upon t, that is 1 upon t is x plus 3y plus 6z. and then del upon del x of t again. This is equals to 1 upon x plus 3y plus 6z, because y and z are independent of x. So, partial derivative of y or z with respect to x will be 0. Now, similarly fy will be again 1 upon t, that is 1 upon x plus 3y plus 6z into del by del y of x plus 3y plus 6z, which is 3 upon x plus 3y plus 6z. Similarly, if you want to compute fz, it is again log t, derivative of log t is 1 upon t, it is 1 upon x plus 3y plus 6z into del by del z of x plus 3y plus 6z, which is 6 upon x plus 3y plus 6z. Okay. So, this is how we can find out del f upon del x, del f upon del y, or del f upon del z. Let us try one more problem based on this, so things will be more clear. So, it is x square plus y square plus z square whole raised to power minus 1 by 2. So, f x will be, now it is t raised to power minus 1 by 2, that will be, derivative of that will be minus 1 by 2 t, which is x square plus y square plus z square, and t minus 1, and del by del x of t again, that is x square plus y square plus z square, which is equal to it is minus 2x upon 2, a derivative of this is 2x, and it is x square plus y square plus z square whole raised to power minus 3 by 2, which is minus x into x square plus y square plus z square whole raised to power minus 3 by 2. Similarly, if you find del f upon del y, it is again minus 1 by 2 x square plus y square plus z square whole raised to power minus 1 by 2, and del by del y of this term, which is 2y, because x and z are independent of y. So, 2 cancel out, and it is minus y into x square, okay, minus 1 again. So, it is x square plus y square plus z square and whole raised to power minus 3 by 2. Okay. And similarly, f z will be minus z x square plus y square plus z square whole raised to power minus 3 by 2. So, this is how we can compute f x, f y, or f z. Now, suppose f x y z is sine hyperbolic x y minus z square. What is sine hyperbolic theta? Sine hyperbolic theta is e raised to power theta minus e raised to power minus theta upon 2, and cos hyperbolic theta is e raised to power theta plus e raised to power minus theta upon 2. Okay. So, we can easily see that d by d theta of sine hyperbolic theta is cos hyperbolic theta, that we can easily see. If we differentiate this respect to theta, it is e raised to power theta, it will become plus e raised to minus theta upon 2, which is cos hyperbolic theta. Okay, that we can easily see. So, if we take f x, which is del f upon del x, now sine hyperbolic theta is cos hyperbolic theta, the derivative of sine hyperbolic theta is cos hyperbolic theta, and del by del x of theta again, it is x y minus z square, which is y into cos hyperbolic x y minus z square. Okay. Now, Fy is similarly it is cos hyperbolic xy minus z square into del by del y of xy minus z square, which is again x times cos hyperbolic xy minus z square, and Fz will be cos hyperbolic xy minus z square into del by del z of xy minus z square, and derivative of this term with respect to z partially, this will be 0, then this will be minus 2z times cos hyperbolic xy minus z square. So, this is how we can compute fx, fy or fz. So, these are some simple illustrations. Now, what is the relation between continuity and partial derivatives? We have already seen what do you mean by continuity of several variable functions, and we have also seen partial derivative of several variable functions. Now, in single variable function, if a function is differentiable at a point, so this implies function will be continuous at that point. We already know this result, that if a function is of single variable and function is differentiable at a point, so this implies function is continuous at a point. If a function is continuous at a point, then the function may or may not be differentiable at that point. Okay. Now, what is the result in multivariable function? Let us see. So, if a function fxy is continuous, if a function fxy is continuous, okay, at a point say p, then the partial derivative fx and fy at p may or may not exist. Also, if fx and fy exist at a point, then the function fxy need not be continuous at a point. So, if a partial derivative of a function fx and fy exists at a point, then it also does not ensure that a function is continuous at that point. Okay. In single variable function, differentiability implies continuity. In several variable function, if the function if the partial derivative exists at a point, it does not mean that a function is also continuous at that point. How we can say this? So, we have counter examples. Let us see. The first example is fxy is equals to, it is x plus y sine of 1 upon x plus y, x plus y should not equal to 0 and 0 when x plus y is equal to 0. Now, first we will see if a function is continuous at a point, then its partial derivative does not exist at that point. This is an example which is continuous at a point 0 comma 0, but partial derivative fx and fy does not exist at that point. So, for continuity, what we have to show? If we are saying that this function is continuous at origin, so what we have to prove? We have to prove that limit xy tending to 0 0 fxy should be equals to f0 0, or this means limit xy tending to 0 0, here fxy is x plus y sine 1 upon x plus y is equals to f0 0 is 0 plus 0 is 0 means 0. So, this we have to show. If we are saying that a function is continuous at a point 0 comma 0 or origin, this means we have to prove this equation. Okay. Now, in order to prove this, we have to use delta epsilon definition. The only option is using delta epsilon definition. So, we will take again, let epsilon greater than 0 be given. Now, take mod of x plus y sine 1 upon x plus y minus 0 fxy minus L. This is equal to mod of x plus y into mod of sine 1 upon x plus y. Okay. Now, sin theta, its mod is always less than equal to 1 for any theta. So, this will be less than equals to mod x plus y into 1, and this is less than equals to mod x plus mod y. Mod a plus b is always less than equals to mod a plus mod b, and if we take it less than delta plus delta, so if we choose 2 delta is equal to epsilon, then mod of x plus y into sine of 1 upon x plus y minus 0 is less than epsilon whenever 0 less than mod x delta less than delta and 0 less than mod y less than delta. So, we have shown the existence of such delta for every epsilon greater than 0 for which this inequality hold. Hence, we can say that the limit of this function is 0 or this equation holds. Okay. This means function is continuous at origin. Okay. So, hence we can say that this function is continuous. Now, we have to find out its first order partial derivatives. Now, since function we can't find its partial derivative as such, we have to use the definition of limit. Okay. Because we have the function in the split form, 0 at 0 0 function has different value, I mean 0 value. So, we have to use fx at 0 0, we have to use definition of limit h tending to 0 f of 0 plus h 0 minus f 0 0 upon h. Okay. By the definition of partial derivative of f respect to x. Now, this is limit h tending to 0. Now, f at h comma 0, we will use this thing which is h plus 0 is h into sine 1 upon h minus f 0 0 is 0 upon h cancels out. So, this is limit h into 0 sine 1 by h, and this is does not exist because it is not a finite value. I mean it is not a unique value, it lying between minus 1 and plus 1, but it is not unique. So, limit does not exist. Similarly, if you find fy at 0 comma 0, so it is limit s tending to 0 f of 0 comma 0 plus h minus f 0 0 upon h, which is again limit s tending to 0. Now, f 0 comma h, so you replace y by h and x by 0. So, it is again h sine 1 by h minus f 0 0 is 0 upon h cancels out, and it is again limit h into 0 sine 1 by h, which is does not exist. So, by this example we have seen that if a function is continuous at a point, it does not mean that the first order partial derivative exists at that point. Okay. Now, another example. Now, using this example, you see that show that a function this is not continuous at origin, but its partial derivative f x and f y exist at origin. Okay. So, first we will prove this. So, it is x raised to power 4 y, or it is x square y upon x raised to power 4 plus y square when x y is not equal to 0 0, and it is 0 when x y are 0 comma 0. Now, first we have to show that this function is not continuous at origin. Okay. So, let us find this limit first, limit x y tending to 0 0, function is x square y upon x raised to power 4 plus y square. Now, to prove that this limit does not exist, we have to show that it is path dependent, that is from two different paths. If we have shown that the value of the limits are different, this means limit does not exist. Now, let us move along say x equal to 0, that means along y axis. If you move along y axis, then you simply substitute x equal to 0 here, which is value is 0. So, it is equal to 0. Okay. If you put x equal to 0, so value is simply 0. Now, you move along say y equal to x square. Now, if you move along y equal to x square, so this will be limit x tending to 0, it is x square into x square upon x raised to power 4 plus x raised to power 4, which is equal to limit x tending to 0, x raised to power 4 upon 2 x raised to power 4, which is 1 by 2. So, we have from this path value is 0, and from this path value is 1 by 2, that is from two different paths values are different. This means that this limit does not exist, and this implies f x y is discontinuous at origin. Okay. Now, let us try to prove that its first order partial derivative exists. Okay. So, let us find f x at 0 comma 0. Again we will use the definition of limit, it is limit s tending to 0 f of 0 plus h comma 0 minus f 0 0 upon h, which is limit s tending to 0. Now, when you put h comma 0 here, x is h, y is 0, as x is h, y is 0. So, simply this value will be 0. So, it is 0 minus 0, f 0 0 is 0 upon h, which is 0. Now, again when you compute f y at 0 comma 0, it is limit s tending to 0 f of 0 comma 0 plus h minus f 0 0 upon h, which is again equal to limit s tending to 0. It is 0 comma h, you replace x by 0, y by h, x by 0, y by h. So, this value will be 0, 0 minus 0 upon h, it is again 0. Okay. So, f x and f y exist at origin, which is 0, value is 0, but we have seen that this function is not continuous at origin. So, existence of partial derivative at a point does not guarantee that a function is continuous at that point also for several variable functions. So, what is the additional condition required? When we can say that beside existing of partial derivative, what are the additional condition which function must have, so that we can say that the function is continuous at that point also. So, that condition is basically if the partial derivative f x and f y or f x y exist and are continuous also throughout a disk centered at a comma b, then function is continuous at that point. That means, beside the existence of partial derivative at a point, we must have continuity of partial derivative throughout a disk centered at that point, then we can say function is continuous at that point. So, thank you very much.